we introduce Swipe Mosaics, a 2D interface to perform content-centric navigation. Our image-based rendering technique converts video, captured with an uncalibrated handheld camera, into this interactive visualization. In the main screen, we can click or touch anywhere on the current frame of the video, and that element of the image now serves as a handle for spatially navigating to other frames. Swiping south is like moving up in the scene, as the system retrieves and crossfades to video frames that are north of where we started. Other directions work the same way, and we can obviously zoom out or into the current frame to see it in full resolution. In the bottom right of the screen, we can show an overview map, indicating the spatial 2D layout of the camera positions as estimated by our system. The highlighted node on the 2D map indicates which image is now on the main screen. The user can switch to what we call the Picasso view, showing all the images overlaid. This view is not intended to be a perfectly aligned mosaic, as we support scenes for which true panoramic mosaicing is impossible. Rather, the aim is to aid the user's sense of navigation. Unlike regular mosaicing algorithms, swipe mosaics are designed to cope with handheld camera footage. This means that the parallax visible in this train track footage doesn't adversely affect the inferred camera transforms or the viewing experience. Swipe mosaics compute the spatial layout of new frames in 2 steps. First, our regression random forest estimates the relative translation between just pairs of images, and then our layout algorithm produces a global 2D coordinate for each image. To work well, a random forest needs substantial amounts of accurate training data. This is where a graphics engine helps. We rendered thousands of pairs of images, like those shown here, and used them to teach our random forest what different 2D camera motions can look like. This input video of a sculpture is challenging in 2 ways, which are not uncommon in homemade footage. The individual frames exhibit motion blur, and the subject itself has little texture where distinct interest points could be tracked. The pose estimates that a leading structure for motion system does compute can certainly be projected for use in the swipe mosaic interface, but the full swipe mosaic pipeline is better at coping with these challenges, localizing all 101 cameras instead of just 38. Deterministic pose estimation algorithms are robust to moderate motion within a scene, but these leaves eventually prove too difficult. Our approach, on the right, is more forgiving, allowing the user to maintain visual continuity while grabbing and swiping different elements. Viewfinder alignment works on many of our sequences, and when it can find transforms, they lead to good swipe mosaics. In this case, however, viewfinder alignment fails to connect the entire sequence together due to a lack of inliers in the corner matching stage. The largest cluster produced for this 200 frame sequence was 94 frames. MicroSFM, however, succeeds in connecting the entire sequence together, giving a good quality of navigation. The featureless obstruction close to the camera causes these baseline algorithms to fail on this video. MicroSFM computes transforms to connect all the frames, but noisy sift matches lead to jarring visual artifacts. Our system places the frames in the correct order for much improved navigation. Automatic gain adjustment can cause short periods of sensor saturation when light intensity sharply increases. These saturated frames cause all feature detectors to fail. None of the baseline algorithms connect the start and end of this sequence together. When given featureless frames, our system outputs proposed transforms with corresponding uncertainty, allowing a full reconstruction that avoids overconfident commitments. Temporally neighbouring frames from a video are fed to our regression and layout steps in the first pass. Based on these initial 2D locations, new pairs of frames may be located close enough to each other to suggest being loop closures. There is no guarantee of convergence in light of error accumulation. Nonetheless, we regress poses for the new pairs and rerun the layout algorithm, which gives an overall improved layout as shown here. Finally, as a post-processing step, neighbouring images can have their orientation adjusted by a second regression forest, where this one was trained on image pairs exhibiting known rotations. To make a swipe mosaic out of footage like this, several existing pose estimation techniques would suffice. But the benefit of getting these estimates from our regression random forest is that users can import an overall wider variety of footage. In scenes that lack parallax or texture, or have repeated structure or have forward camera motion or scale changes or large occluders, our one algorithm estimates only what it needs and expresses its uncertainty. The output then degrades gracefully if the situation becomes difficult. Here, the user can browse the flowers on display, despite this being an acknowledged failure case for a state-of-the-art camera stabilization algorithm. So far, we and our volunteers have created dozens of swipe mosaics with different potential uses. Swipe mosaics should easily lend themselves to online shopping and auctions, large-scale inspection and remodeling projects, and various personal applications. For the remaining videos we have tested, content-centric navigation now seems straightforward and a natural way for browsing footage for details and spatial relationships. To run a swipe mosaic visualization, devices must accept a click and drag or equivalent interaction, have low latency, and have graphics memory proportional to the images being viewed. Filming and building swipe mosaics is easy and will hopefully open the door for many content creators who want to document, annotate, and share the details of the world around them.